All right, so with the beginning of a new semester, okay, I've always had the, let's say, impression, at least for me in my mind, when you talk about, not that, how I want to state this, I'm looking at my lesson plan board, and as far as each class is concerned, there's probably going to be some aspects that are maybe more important than others. I'm trying to think with organic chemistry what that might be. My guess would be the aromatic compounds, maybe that, and then you say it's all important. Well, yeah, it is. But with this class, maybe stoichiometry, I've always had, like I said, the impression or idea that this is pretty much the entire backbone of what general chemistry actually is. You're taking a lot of the information that you have learned last semester, and then you're applying it to this semester. Now, whether that's going to be what we see tomorrow with mole to mole calculations or mole to mass, that doesn't mean anything to you right now, but we'll go ahead and apply that information. You know what a mole actually is. It's just a counting unit more than anything else. The most popular, let's say, what I think is the most popular example is I always take something that can hold 32 grams of sulfur in here. And why would the idea of 32 grams of sulfur be important? Because that's going to equal a what of sulfur? It's going to be 1 mole. Okay. Remember, moles are just counting units, and you're going to be applying that with chemical reactions. So that's why we say this is probably the entire backbone of what general chemistry is. Half of this is doing these dimensional analysis problems. Then the second half deals with limiting reactants and percent yields. And it is one of those aspects. Well, you don't want to fall behind in any class because it's not going to be very conducive to being successful. But and of course, this is no exception. It's one of those times where if you do fall behind, it's pretty tough to get caught up. Okay. The example I told with the freshmen, maybe not that you're following different types of football, but for instance, the Cotton Bowl was on last night, and was it Texas and Georgia? Yeah. So it was one of them scores where in the fourth quarter it was Georgia might have still had a chance. It was 28-14. I'm guessing Texas won because again Georgia was trailing by 14. And when you do that towards the end of a season, whether it's volleyball, football, when you fall behind in the postseason, it's really difficult to play catch up. If you're behind, yeah, it just magnifies the opportunity of trying to get caught up. So, should you feel that you're not understanding this, please, you've got to say something. Otherwise, if you don't, we just keep right on going. I mean, and I think that's the right thing to do. So, when we're applying these, I think if you're not good at balancing chemical reactions, even for instance, let's say you're finding the amount of, like last semester, you're finding the amount of substance in a material or a compound, and let's say we talked about rust and iron 2 oxide. What's the difference between iron 2 and iron 3 oxide, for instance? If this is iron 2, how do we make this one iron 3? Okay? So what we're saying back there, if it's iron 3, it's got a +3 charge. So in a word problem, when this deals with a chemical reaction, should you not get these little numbers right? 2, 3, 4, maybe 5 steps down the road, it doesn't matter what you do, it's going to be wrong. So if you don't get it correct at the very beginning, yeah, and it's unfortunate, but it's not like I think maybe you can appreciate like each one of those problems. Let's say it was worth 8 points. Typically, what we could say, if you get it wrong, it's -8. Would that be awful? Why is that? You got it wrong. It's yeah, it'd be everyone's in the same boat, so it's not a let's say we're not singling anybody out. Is that the way it is in math? Do you get partial credit? Do you deserve partial credit? I'm not saying you should or shouldn't, but okay. Why? Just out of curiosity, why would you state it that way? It's up for debate. Why is that? No. Why is it up for debate that you should or shouldn't get partial credit? Why don't you deserve it? That's why I'm asking. Mm-hmm. 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 But you know how long and tedious it is to do that, to look through each and every paper, and if we just grading would be so much easier. Just say it's wrong. -8. Just move on. Right on down. How do you differentiate between who deserves it and who doesn't then? Is it because of the work? Okay. So the reason that that could be difficult is, let's say there's 2 of you in here who are battling for, they still do valedictorian salute. They don't do that anymore, do they? But let's say, for argument's sake, that they do. You do that, well then, is that in every class or just this? What you just said? No, give everyone A. Oh, okay. But I've had many students in the past say, this is something that you do not want to fall behind in. I can't stress that enough. Because if you're coming in here, you're working on other home, not that everyone is right now, because we're just starting. You don't even know what the stoichiometry is. If it's one of them things to where, when we're down to, let's say, January 15th, and we're getting into just getting done with mass calculations, and then moving on to limiting reactants, if we haven't mastered this part, it's really difficult to move on to the next part and actually understand it. Okay? And no one's doing the wrong thing. It's an old, I don't know what to call it, an army adage, is just do the right thing. So at what age, if that is the case, at what age does that actually sink in? Do you know that as 8th graders? Do you know that as freshmen? Do you know that as sophomores? Because you probably do know that as juniors. So if you do, when did that start? Coming in and just doing what you're told, and if someone else is asking a question, you're not talking about having sidebar conversations and things like that. That's what I'm getting at.
Say freshman year, like we were in your stuff, I feel like freshman year was really easy. And so they were still like kind of into having, I feel like sophomore year, they're like, okay, you ain't got time to mess around. And then the junior year, you just fight to stay alive. And then senior year, you're like, I'm almost done. Like, I don't have time for anything else. I'm just going to
Okay.
listen.
Okay. So, but why does it take that long then? Why can't it be? And I get it when it comes to 7th and 8th graders. That's a trying time because the human body is going through so many different changes that you just don't realize. Now we're talking about a physiological aspect. So so yeah, I get that. But then when you're a freshman, it's kind of like it would be so much easier for everyone involved. Just come in, you just sit down, and
Maybe it's like, particularly with teenagers, they have to do a lot with like pediatrics.
Well,
Like,
also they're like risk take, like it's proven that like younger like teenagers like take more risks and they don't really like know the like
consequences
yeah
to that.
of their actions and
Hmm.
they don't like look to the future like maybe like juniors and stuff are like more aware that like we got college in a few years so like we need to pay attention and that
So then,
freshman year
if someone told you that when you're a freshman, why not listen?
because they're still like they're just like oh that's so
5 years.
far
Yeah,
away
it doesn't
that's not
really
gonna
like.
affect me.
But then, and how many times do you think? I don't think it's anybody in here, but how many times do you suppose it happens? The change from the freshman year to the seniors. Why didn't I do this when I was younger? Well, we told you, but you wouldn't listen. So then, how does a person move forward from that?
At least in my experience, freshman and sophomore years, I didn't feel like college was ever going to be a thing. I just felt like I had to worry about it later. And then now it's freaking me out a lot.
Okay.
I
I
think the
think
stress about college more like freshman year. Like it hit me hard when I was a freshman. I was like, 4 years I will live at home. And now I'm just like, okay, I can.
Okay. Anyway,
This quarantine made me want to
enough of that. Page 299. 299.
make special teams.
right.
Yes.
Are we gonna be able to do another lab again this year?
I don't
Yes.
know.
Really?
Not as long as what last semester's was. Yeah. Okay. So on page 299, Introduction to Stoichiometry. Okay. Much of our knowledge of chemistry is based on careful quantitative analysis. Okay. Of substances involved in chemical reactions. That's why we end this semester with uh, chemical reactions, because, as it says, we did composition stoichiometry, which was just changing a mass of a substance into moles, or a certain amount of moles into a mass, and that was it. Okay, just simple two-step problems. It maybe became a little more complex when we started talking about molar mass problems and that of percent compositions. Because if, and again, if we do things the way that we want you to or instruct you to do them, you're going to make things a lot easier on yourself. Because what we ended with last semester is how we're going to start this one, especially with the molar mass problems. Okay? Because remember when we said in this step, step 3, how many of you remember why was step 3 so important?
I thought we had to like divide by anything.
No. It allows you to change what you have to what you're actually looking for.
Oh, okay, never mind, never mind.
Okay? So now we're getting past that composition stoichiometry like you learned in chapter 3, the mole to mass, mass to mole. Now we deal with reaction stoichiometry. Okay? It involves the mass relationships between reactants and products in a chemical reaction. And that is how this is different than last semester. Okay. So reaction stoichiometry is the subject of this chapter. It is based on chemical equations and the law of conservation of mass. all reaction stoichiometry calculations start with a balanced chemical equation. So if you can't balance that chemical equation, there again, or even the compound, what it's saying is anything beyond that, doesn't matter what you do, it's going to be wrong. And that's not me standing up here, you are wrong. Well, there's a little more black and there's a little more of a gray area, if you want to call that, to where if you're illustrating what you know, that's why you're getting -4 on a problem rather than -8. Okay? Because it is one of them things, to believe it or not, we're trying to instruct this to younger individuals. Believe it or not, we want to see you succeed, but sometimes you just say, throw us a bone here. What does that mean? Well, yeah, I mean, if an opportunity is afforded to you, you really should take advantage of it. Okay? And so that's why we say, come on, show us an effort. Come in and ask questions or something to that effect. That's what we mean by throw us a bone. Okay. So, with reaction stoichiometry problems, we're not going to spend a whole lot of time on reading all this material, but okay, the reaction stoichiometry problems in this chapter can be classified according to the information given in the problem and the information you expected to find, the unknown. The given and unknown may be both the reactants, they may both be the products, or one may be a reactant and the other a product. What that means, especially when you're dealing with the reactants, one of the things that we had talked about was you're going to do mole-to-mole calculations, and mass-to-mass calculations are the longest ones. So that's the first part of stoichiometry. And then the second part we said was limiting reactants and percent yields. That means you're dealing with maybe just the reactant side. You're going to see what runs out first, because that's what a limiting reactant is. It doesn't mean that you can't form a substance. It just means you are limited to what you can form. That's why it's called the limiting reactant. And sometimes when we picture that, how can we give an example of something that is limited? For instance, if what popped in my mind is, let's say, a landowner that just lives on an acreage and doesn't do any farming, okay? But they do have a tractor. It's a little utility tractor with about maybe 40 horsepower. And the person that you, or farmer that you rent that land out to, has a couple of, let's say they got a couple gravity wagons out there that, God, we can't quite get to the farm place tonight, but if you could go out and pull those wagons home and get them in the yard for me, that would be great. Now, a little 40 horsepower tractor, can that do the job if the wagons are empty? Sure, it can do it if they're empty. Heck, you people can even pull an empty gravity wagon. I mean, not say that you can do it very long or for very far, but you could. But the limiting part of that would be if those wagons are full, and these are what's maybe 300, some of them maybe 650 bushels. If those are full, you got a little 40 horsepower tractor, your wheels are going to start spinning. You're going to start digging a hole down in the ground. Okay, so in that case, you're limited on what you can actually do. Okay. So that's kind of what limiting reactants actually are. Okay, so problem type 1. Okay, given and unknown quantities are amounts in moles. Okay, so that's why we see tomorrow we're going to start talking about mole to mole calculations. Okay, so when you're given an amount of a substance in moles and asked to calculate the amount in moles of another substance in chemical reaction, the general plan is amount of a given substance in moles. It's a two-step problem to an amount of a substance in moles as well. In other words, you see one arrow, okay, 2 steps. When you get down to problem type number 2, it's going from moles to mass. Okay? So in that case, you see 2 arrows. That's going to be a 3-step problem. Okay? And then there's another type of 3-step where you're going from mass of a substance to an amount in moles. And then the most complex, problem type 4, given as a mass in grams and an unknown mass is also in grams. And that's one of your activities that you'll be doing probably 2 weeks out, I would say, at the earliest. And it's a dual step process. One, you're given two reactants. Okay? You need to calculate how much of a product is formed, and then you also have to determine, well, what's the limiting reactant. Okay? So, like for instance, if you look in this class, you know each other better than perhaps anybody else. So who's the weakest link, do you think, if we call it the weakest link? Who's maybe takes the longest to understand this material?
No, it's definitely me. I was gonna say college. Oh, sure. Yeah, it's probably me.
So it used to be when I was still at Dakota State, um, they used to have what was called the math and science contest. They don't do that anymore. Well, it was an opportunity to go there and apply for a scholarship. Now the problem with that is if you wanted it, you actually had to attend the university. But so if we were to go head to head with another school, that's what we ask. Who's the weakest link in here? Okay.
Jordan. Yeah.
Okay. So what that means is you're limited to what you can do. Again, just like that tractor. It's a little 40 horsepower. You're probably not going to be able to do a whole lot. You're limited on what you can actually do. Okay. And that again is what a lot of reaction stoichiometry deals with. Okay. And if we're still confused on what the mole is, sometimes when we say it's a counting unit, which it is, you go back to that cup, sulfur, we got 32 grams in there, we have approximately 1 mole. And in referring to this as a counting unit, one thing we could say is if this sheet of plywood here, if it's not cut this way, we can infer that it's probably how many feet? Say that again. 8 feet. Okay? Because when you get full sheets of plywood, they're usually 4 feet by 8 feet. Okay? 96 inches. It's a lot easier to say 8 feet than it is 96 inches. Or if you're looking at the area on the wall here, it's a lot easier saying, and I don't know how accurate this is, it's a lot easier saying, well, it's probably about 20 feet by 25 feet. A lot easier referring to the square footage than the square inches. I mean, because the math is a lot simpler. I think when you look at 20 by 20 and say it's 400 square feet, it's a lot easier with the math because anybody can do 20 times 20.
It takes me a minute.
Oh, okay. But if you convert that to inches instead, that's what, 240? Well, then taking 240 times 240, that's a little more difficult. Okay? Well, don't compare yourself to a meter. You always come up a foot short. No, that's actually not a foot. 4 inches short. Yeah. Yep. So with that, again, don't get hung up on what a mole is. It's just a counting substance. Just like when you measure 36 inches, it's 3 feet. That 3 is just a counting unit. That's all that a mole is. Okay, so we've done a little bit of reaction stoichiometry. The last thing we want to do is, and I think you might not agree with this, but you're not always going to be given the equation all the time. I mean, sometimes it's given in a word format. And I guarantee you, especially when we get to gas stoichiometry, the problem with this is, and I say this as well, if general stoichiometry beats you up pretty bad, gas stoichiometry is going to finish you off. Guaranteed. Okay? So it's kind of like one of the things I think about is, has anyone ever seen the movie Casino? You ever heard of it? And it's Joe Pesci. He's the gangster in there, and he's talking about how beating up this witness or whatever, and he says, you know, I'm not afraid to beat you up. I'll just knock you over the head with a shovel, knock you into a coma. And then by the time you get out of the hospital and I get out of jail, I'm going to take the shovel again and wallop you over the head and finish you off. That's what stoichiometry does to people. What this doesn't, if this doesn't finish you off, gas stoichiometry certainly can. Now, what that means is, what you need to think, is he really bluffing? Do you really want to lay the cards on the table and find out? Okay? So, now don't blurt the answer out here. Okay? Just follow along. Okay? So, hydrogen chloride. Maybe this is kind of hard to see on, I think we can see it on the presentation. So, now, this is a very simple equation. Okay, so just by looking, now be honest, because if you're going to be one of those, now it's easy to do that. Say, yeah, I would have got that. Looking at this, how many of you may have forgotten those little subscripts?
I forgot that.
If you forget that, there again, okay? Because if we're looking for something that has to deal with this over here, okay? Because maybe you forgot to put that coefficient. Again, that's just a counting unit, okay? Because if you're doing a mole-to-mole ratio, just like with that measuring tape, 36 inches is 3 feet, or 24 inches is 2 feet. It's just a counting unit, okay? So if you're trying to convert this substance into this, and you don't have that because you didn't balance it correct, it doesn't matter what you do beyond that. It's all wrong, okay? So that's what I mean. It's going to be an attention to detail, okay? And just like adding subscripts on, or not subscripts, but atomic mass units. If we're dealing with something like lead acetate, okay? You know, it's very easy to make a mistake with that because this compound looks like it's so big. You may forget to double it. There's a whole set of things you can forget to do. Okay? And sometimes, again, what happens is when these aren't put together, people may look at this and say, oh, well, we've got 2 oxygens. Well, that's true for that one, but then they forget about this one. Not always, but it can happen. Okay? So, that's just a brief introduction what stoichiometry is, and we'll continue with this tomorrow.
Can I have a quick question?
Okay?
Diatomics are the stuff that
Any gas and column 7 elements with the exception of noble gases. Noble gas is already stable. So